Okay, we'll be starting the recording now. And first thing we want to do is create fractions for each of these equalities. And I'm going to give you a shot at it where you can see right now what that is going to look like. We're making an equality into a fraction like we've done since August. So stop the recording and do that for yourself, and then come back and check it out. Okay, coming back, and we're in class right now, so we'll go ahead and call on people. So Sassoon, what do you have for the two fractions for the first one?
1j
Over.
0.23.
Good. And the second fraction looks like?
Take it for second fraction.
No problem. It's upside down.
Oh.
Oh, okay. Small hops. Good.
That's trippy.
Okay. Why? Because sometimes, like for this guy right here, if you're starting with calories, and if calories were your given, then you'd want calories on the bottom, right? But if joules was your given, then you'd want joules on the bottom, and your fraction would look like this one over here. Does that make sense? That's what this is all about. Okay? And let's move on. Height, what do you have for your two fractions? Over. Yeah. Okay, good. And the other fraction is? Yeah. Okay, just upside down. Very good. And Colleen? Okay, good. And do you all remember this little trick where we have K here? What does K stand for? Kilo, but it's what? How many zeros in kilos? 3. And that's what this is all about. See, we're substituting the K with 1,000. So we started with this guy. We drop out the K and put in what it means. And that's how you make your conversion fraction, which then can be conversion equality, which then becomes your conversion fractions. And Alexa, what do you have? For calories? The big calories.
1 calorie.
Mega calories, yeah. Okay, good. 1 calorie with a capital C over 1 kcal. Kcal, whatever. Radio station. Radio Kali. All right, you know what the other fraction is? Good. Okay. So, what we're going to be doing today is learning how to do problems that involve specific heat. And specific heat is something that allows us to measure what's going on as we heat things. They get hot. But it also lets us measure what happens when we cool them. What is a device that you have in your home that will cool things?
The air conditioner.
Refrigerator or the air conditioner. Yeah, they both work the same way. Okay? So, that is the formula that we're going to use in all of these problems. So you want to get that formula down, and then we'll do the means of each. We'll start out with heat absorbed or released. And what's the unit of measure for that?
Q.
Yeah, what's the unit of measure? Q is the thing that specifies. Well, what? Yeah, joules. J. Okay, joules. J. J is the abbreviation for joules. Now, we got to understand what we mean by absorb or release.
Use J for heat.
J is for heat. Yep. And heat energy of one kind or another. So let's take our package of hamburgers that's in the freezer. Today we're going to have a party, right? And we are going to have to change those a little bit. How do we change them so that they're edible?
Cook them.
We cook them with heat. Okay, so what are you going to cook it in?
Fire.
Fire. Oh, you're going to do microwave. Oh, can you imagine a hamburger done in a microwave? Ugh.
I've had one before.
I know. It's not so bad. All right, so now, when we put it on the grill, or when we put it in the pan, is the meat absorbing heat or releasing heat? Absorbing. Absorbing. If it absorbs heat, is the temperature going to go up or down? Yeah. More heat, more temp. So, when it's released, where's that going to happen? We put it in the refrigerator. If it's a leftover, anything left over, if we're going to save it, we put it in the refrigerator. And so, in the refrigerator, it's what? Absorbing or releasing heat? Releasing. And the refrigerator has coils inside the refrigerator that go to the outside of the refrigerator, and there's a compressor in between. And on one end of the compressor, it's cold. On the other end of the compressor, it's hot. Have you ever felt behind a refrigerator?
Yeah, it's hot.
And you think, oh goodness, this is a refrigerator. It's supposed to be cold. Not outside. It's a heat pump. It literally pumps the heat out because it's not a chemical reaction. It's simply compressing and expanding. And it requires a motor to run that pump so that the Freon, which is what they used to use, they have other refrigerants now, but the Freon gets pumped into a smaller tube by the compressor, which makes it absorb heat, and then it gets sucked into a larger one on the other side of the compressor, and it releases the heat out there, which is fortunately the outside. Yes? You gotta have the coils. No, you gotta have the coils to have the areas to release either release the heat or absorb the energy. And inside, we're absorbing energy on the coils, and the heat is coming from the energy is coming from the warmer stuff that we put inside. And so it takes the heat from inside and it releases it on the outside. That's very, very neat stuff. Okay, down here. That's an easy one. M per mass. Very, very simple. Mass in grams. Because wouldn't you say it would take more heat to heat up 1,000 gallons of water than it would to heat up 1 gallon of water? Oh, yeah. Yeah, a whole lot more. Yeah. Okay, so the mass is important when we're thinking about the specific heat, which has mass as one of its components. You should be writing this down. You won't understand this if you don't. Okay, a temperature change is just that. It's a change. This is not a temperature.
Is it temperature K?
Yeah, that's kelvins. We're talking about centigrade in these calculations. So delta means change. Change temperature. This guy is a temperature change. Now, they could ask you two different ways in a question. They could say, what is the temperature change? Or they could say, what was the original temperature? Or what was the ending temperature? If you know that the temperature change was a line this long, and that's the change, it's going from point A to point B, And A could be something like 5 degrees centigrade, and B could be, say, 40 degrees centigrade. Okay, going from point A to point B on the temperature scale. Okay, that's a change of how many degrees? 35, right. So if I told you what the starting temperature was, when you do your calculation, you're not getting the answer. You're getting the change. So if the temperature change turned out to be, in this case, what was it? 35. So if the temperature change is 35 and my starting temperature is 5, that's where we get our 40 from for point B. We're looking at a thermometer. Okay? And then specific heat is this guy. Whoa, look at all those letters. Joules per grams degrees centigrade. How in the world do they come up with that? They take 1 gram of a substance. They take 1 degree change in the substance, and they record how many joules it takes. How much energy does it take to heat it up or cool it by, say, 35 degrees? So that's all there is. It's just recording data from an experiment. Could you close the door in the back, please? And now let's do some problems. I'd like you to write this problem down, but don't write the problem down. Write down the given and the find. This is your 4th homework problem, by the way. So if you start a fresh piece of paper, I'd start on the back. You can do your first 3 problems on the front. Yeah. And this would be the 3 PP variety. 3 problems per page, per side. Okay, can you all see this? Can you read it okay? So if the temperature of the ethanol, 34.4 degrees of it, increases from 25 to, okay, what's the delta T?
34.4.
I think it would be 35.8 or 55.8. You're subtracting 25 from 78, right? 53.8. Okay, so that's your delta T. And how much heat has been absorbed by the ethanol? Guess what? We've got this wonderful little thing called a specific heat chart. Ooh, is ethanol on this chart?
Yeah.
Look! Yeah, ethanol's there. And what does that L in the bracket mean? Yeah, that's liquid. Good. So, what is the specific heat? Yeah, that's in your book. It's on page 492 in your CMC book. Okay, here we go. Let's look at problem number 4, and let's kind of cover this up for a minute so we can focus. And let's see if we got something that we can use. All right, let's take Edgar. You're on. Okay, Edgar, what do you have for your given? Your first given. What? Okay, and the mass is? Good. Okay, so we got M equals, this is how I want to see your homework done. 34.4. Oh, absolutely. You'll get totally lost if you don't. Okay, so we've got our mass, and Christian, not here. William, do you have another given? What else is given? Come on, we just went through them. Well, you're close. 53.8. 53.8 is our delta T. And Janet is not here. Alfredo's not here. Wow. Cassandra, what do you have for one more variable? Do we have one more? Ah, good. The specific heat. Had to get that out of the table, didn't we? Here we go. Now it's plug and play. And, what are we supposed to find? Okay, here's the formula. Okay, so, is this what we're looking for?
Yeah.
Well, let's see. What is the find? David, String? What's our find? What are we looking for? Heat. Yes. And heat is Q, and the unit of measure for Q is joules. So what we want to do is write this guy out, and then we fill it in as we see down here. Okay, so these guys, this comes from our given, and this one comes from our given for the mass, and this is our temperature change. Now, what are we don't have to find a final temperature on this one. We're just looking for the joules for a particular temperature change. And this, you notice that was liquid. And when you get solid or gas, the specific heats will change as you go from solid to liquid to gas. It's called a heating curve. And it's different for every substance. So when we're done with this guy, we come up with, there we go, this guy here, which is the joules that you get when you multiply this guy times this guy times this guy. And you get this on your calculator. Now in the textbook, it gave us the answer like this. So where did this 3 come from? How did we get 10 to the 3? Yeah, you got it. Okay, this guy right here is not a decimal. The decimal is here originally, right? And so we moved it over 3 to the left. So a positive 3 as an exponent on 10, we'll move it back to where it was. We'll move it back where it was. We'll move it back right where it was.
That's a real song?
Yeah, I just made it up.
Oh.
I do that all the time. You'll get used to it. All right. So, here we go. Number 5. All right. We'll do the same thing. Let's get the given and the find. Be sure you leave yourself about a third of a page for each of these problems, because these need the space. Okay, we have... Okay, we're looking for a final temperature, aren't we? So, Matt, if we get our delta T, have we found the answer?
No.
That was the temperature change, wasn't it?
Yeah.
Okay. So what do we have to do with the temperature change to get the final answer? You have to run a calculation and find the change in temperature, right? And you're going to use the formula that you see right at the top of the page, correct? And for right now, let's go ahead and close this off so we can focus a little better. So what are we going to do? Specific heat times mass times, well, you're not going to get temperature change. So we got to figure this guy out first. Let's go over here and figure this out. What is our formula? Q, which is what? Okay, that Q is J, right? Joule. Okay, what's the next one? Equals C. What is C? Specific heat times mass, M, times temperature change, which is a delta T. And that's in degrees centigrade. Now, let's look at all of our givens and finds. Okay, that was pretty easy, wasn't it? Yeah, okay. So, Lizzie, what do we have as another given? Okay, good. 276 joules is absorbed. Oh, it's absorbed, so what's going to happen to the temperature? Is it going to go up or down? Yeah. If it's absorbing energy, it's getting warmer, right? And by the way, this is actually a homework problem. If you're not writing this down, you got a screw loose. Okay? So say, what do you have for the last given? Come on, they've given you something else. Here, here's the problem again. What else are we given? Yes, is that a temperature change, or what is it? What kind of temperature is this? Initial temperature. Good, excellent. So we know that this is the specific heat. We were given that, right? And there's our starting temperature. And we know that the heat is absorbed. We have that right here. It says heat absorbed. Is that all together, I hope? Yes, it is. Okay? So the heat is absorbed. And Natalie, what are we going to have for a find? The final temperature, but before we get the new temperature, or the final temperature, as you said, we would have to find the delta T. No delta T? Oh, you stinker. Came apart. Okay. There it is. Okay. You cannot find the new temperature until you get the change in temperature. So when you solve for delta T, you have not got the answer. Or you don't have the answer. Better English. Sorry, English teachers. So, let's solve. How are we going to do that? Lewis, what do you think? How are we going to solve? No, we're going to, when I say solve, I mean here. Because we don't have our find on one side, all by itself. No, before you plug them in. It's going to be easier if you do this first. Get delta T separated. So what do we have to divide both sides by? C and M. Good. Okay. So I'm going to take C times M, and I'm going to divide that on both sides. C times M. Okay, so my new formula, and I recommend you do it this way in all your problems. So the new formula is going to be Q over C times M is equal to the delta T. See, now you're set. You don't have to drag big numbers around while you're doing this. It makes it a lot easier. So now we can plug and play. So here we go. Q. What do we have for Q? What is Q? Joules. Yeah. So we're going to have joules, which is 276 joules. Look what we're going to have. Let's see. Okay, so we have 0.129 joules. Now when we have something underneath the joules, it's going to go on the top. Does everybody understand that? When I divide the joules, which is this guy, over grams degrees centigrade, which would normally go down here, it actually gets flipped and comes up here. And so this is going to be times the, grams degrees centigrade. Joules times grams degrees centigrade. Yeah? Yeah. And over here, or down here, Joules times per inch per centigrade. Yes.
There's no fun.
Yes, there is. There's the M. You got grams here. You know what? I think I want to try that down below. Okay, so what I've done is I've rewritten the fraction to show the stuff in the correct places. And notice we get to cancel the grams. We get to cancel the joules. And what's the only unit of measure left?
Celsius.
Degree Celsius. And that's the temperature change. Okay, when you divide all that out, this is what you get for your degrees centigrade. And that's your change. So we take that and we add it to the starting temperature, which was over here. Okay, our starting temperature was 25.0. And when we put that in here, we wind up with 475 plus 25 is equal to 500 degrees centigrade. And if you wrote that in scientific notation, it would be 5.00 times 10 squared. And that would be degrees centigrade. And that would be the final temperature. Hope you find this helpful.